All right, so in today's lesson, we are going to be just using logarithms to help us solve equations, really building off of the work that we did in yesterday's examples. Let's just start by formalizing the first process we used, using logarithms to solve exponential equations. We're going to isolate the base and exponent. We won't always have to do this. Sometimes the problem will start with that. Once we have that, we rewrite in logarithmic form. Then we can evaluate the logarithm by changing the base and solve for the variable. Again, that might not be something we always need to do. Steps 1 and 4 will kind of depend on the structure of the problem. So let's just go into example 1 here. We have 6, the r equals 51. So if we rewrite that as a logarithm, we get log base 6 of 51 equals r. And then we can use that change of base formula to just calculate what r is. We get log of 51 divided by log of 6. And that equals r. So our answer is, if I plug that into my calculator, log of 51 divided by log of 6, we get 2.19 as our answer. Now, we saw this one yesterday, example 2, a little more complicated just because we have this x plus 6 as our exponent. But we're going to go through it the exact same way we did example 1 and go log base 2 of 6. And that, I'll color code this a little better actually, that x plus 6, our exponent, the entire thing is going to be what our logarithm is equal to. So just got to make sure we carry that whole thing over. Then we can kind of evaluate the logarithm. So log of 6 divided by log of 2. That all equals x plus 6. We do log of 6 divided by log of 2. We get 2.58 equals x plus 6. And then we're subtracting 6 from both sides here to close this out and get x all by itself. So my x value is equal to 2.58 minus 6 is negative 3.42. Is our answer there. Now, what we started seeing yesterday, but didn't dive fully in, was what happens when we have some other stuff going on, like this plus 3 that happens outside of our base and exponent. What we want to do is we want to try to get all of this by itself and move that 3 over, so then we can rewrite in logarithmic form. So before we rewrite in logarithmic form, let's just move that over. Let's subtract 3 from both sides, and we will get 9 to the n plus 10 equals 78. Okay, then we can take that logarithmic form. So we can go log base 9 of 78 equals n plus 10. We can rewrite in changing the base. So log of 78 divided by log of 9 equals n plus 10. And so we run that calculation, log of 78 divided by log of 9. 1.98 is our answer on the left, equals n plus 10. And we just need to subtract 10 from both sides then to get our final answer for n. And we should get negative 8.02 equals n. So you can see this is even a little more complicated with example 4. I wanted to make sure you guys get exposure to some of the hardest problems in these examples. And we're not always going to know what's going to happen. We can't see every possibility. So just be on the lookout for things and make sure that we are trying to isolate this 4 to the x so we can rewrite stuff in logarithmic form. So let me erase that here. I want to leave my work on the other side. So we're going to start by just adding 1 to both sides over here. We get 2 times 4 to the x equals 128. Okay, then we can divide by 2 on both sides to get that by itself. So we get 4 to the x equals 64. And then you guys might just know this right off the bat. You can manually say, hey, I know that x is equal to 3 here. Or if you wanted to, you could keep going down and do our log of 64 base 4, forgot to include that, equals x, which is log of 64 divided by log of 4 equals x. And that just gives us our value of 3 as our answer once we plug that into our calculator. So we can use logarithms to help us analyze some of the word problems and investment problems that we worked with last week. So let's look at example 5. A $100 deposit is made into a bank that pays 12% interest per year. The money in the account A can be represented with the following function. I'm going to make this a little bigger just so we can see it. A equals 100 times 1.12 raised to the t power, where t is the time in years. How long will it take to reach $2,000? So as opposed to guessing and checking and plugging in a bunch of values for t, we can take this $2,000 and swap it into our formula. We know that, hey, the amount I'm targeting is 2,000, and I'm trying to solve for t here. So if I swap that out in my equation, okay, and then I have 2,000 equals 100 times 1.12 to the t, then we want to try to isolate this 1.12 to the t power. So we can divide by 100 on the right, divide by 100 on the left. Okay, we'll get 2,000 divided by 100 is 20, equals that 1.12 to the t power. And then we can rewrite the logarithm. It looks a little different because we have the stuff flipped to the right and left, but we're still going to work it the same, right? Our base is 1.12. My argument is 20. And the thing I'm solving for is t. So we set that up. Let's move over to a change of base formula here. So we can actually solve this. Log of 20 divided by the log of 1.12. That equals t. Oh, I'm losing my ability to write. So we plug that in and we get a value that t equals 26.4 years is how long it would take us to reach that $2,000 goal. All right. The other skill we worked on yesterday was solving exponential equations without logarithms. So when we did this, we wanted to rewrite the problem so the bases were exactly the same. Then we were able to set the exponents equal to each other, and from there solve for the variable. This first step may not always be necessary. We might already have a problem where the bases are the same. So let's start working through this. Example 6. 6 to the x plus 1 equals 6 to the third. If we look here, we see that, hey, the bases are the same. They're both 6. So I am just going to ignore them. I'm going to take down this x plus 1, this 3, and I'm just going to set them equal to each other. X plus 1 equals 3. From there, we can subtract 1 from both sides and just get x equals 2. That one's pretty straightforward. Example 7 just takes a more extreme version of that. All right, I have my base of 4 on both sides. Okay, so I can ignore that completely and take down these exponents 2p and set it equal to the other exponent, negative 2p minus 1. From there, we're using our algebra skills, and this is a good day to just practice this. Even if we don't perfect it, we're going to kind of combine like terms by adding 2p to both sides. So we get 4p equals negative 1. And then we can divide by 4 on both sides, and we'll get a value of p equals negative 0.25. All right, these last two problems, we have to kind of change the base, which we saw yesterday. You'll notice that, hey, 16 and 2 are not the same base. So we can't, 16 and 2 aren't the same. We can't say x equals x plus 1. That does not work. So let's clear this out. And let's think about how I can rewrite this 16 as 2 to some power. And that power that we chose was 2 to the fourth. And if we do that, we can then plug it in. Okay, let's do exactly that. Let's go 2 to the fourth power. And then rewrite everything else to the x equals 2 to the x plus 1. And now we have a situation where, hey, our bases are the same now. We have a base of 2, a base of 2. So we got to do some quick work to combine the exponents. So 2 to the 4x equals 2 to the x plus 1. But now we have a spot where we can take these and set a new equation together. 4x equals x plus 1. And then we can solve for x. So in this case, we move an x over to combine like terms. We get 3x equals 1. And then we can divide by 3 on both sides and get x equals 0.33. Or you can leave it as a fraction, x equals 1/3. So let's try that one more time. I'm going to clear my notes. Well, no, we still have space over here. If we look over here, we have a base of 2 and we have a base of 8. So we want to rewrite this base of 8 as something with the base of 2. So we do that, and that would be 2 to the third power. So that is what's going to plug in for my 8 when I rewrite my equation. We'll go 2 to the 4x plus 1 equals 2 to the third power to the x minus 2. Now, the left side we can leave exactly as is, 2 to the 4x plus 1. The right side, however, we're going to have to distribute that 3 out so it hits both the x and the negative 2. So we get 2 to the 3x minus 6. Then we have a situation where we can set those exponents equal to each other. 4x plus 1 equals 3x minus 6. And then we're going to start solving to get x all by itself. We can subtract 3x from the right and the left. In the meantime, we can also move that 1 over. Let's do that in one step. Let's move that 1 over to the other side. So if we work through that, 4x minus 3x is x. 1 minus 1 is 0. 3x minus 3x is 0. And negative 6 minus 1 is negative 7. So our answer is x equals negative 7.